Why does ice feel slippery? The physics will shock you. You've slipped on ice. Maybe it was embarrassing. Maybe it hurt. Maybe it was both at the same time. But here's what I want you to do right now. I want you to explain to me, in plain words, why ice is slippery. Take your time. You've been around ice your whole life. You've held it, walked on it, dropped it into a glass, skated on it if you're lucky. You know what it feels like. So, why is it slippery? Most people say one of three things. It's wet, it's smooth, or it melts when you stand on it. All three are wrong. Not partially wrong. Not wrong in a technical, academic, doesn't really matter way. Wrong in the way that physicists have been arguing about this for over 150 years and still haven't fully settled it. 150 years. Think about that. We split the atom. We landed on the moon. We mapped the human genome. And we could not agree on why your feet slide out from under you on a frozen puddle. Let's start with the most common answer. Ice is slippery because it's wet, because there's a thin film of water on the surface. Okay, but why is there water on the surface? You press on it, some people say. Your weight melts the surface. But here's the problem. Ice rinks are slippery before anyone skates on them. A frozen lake is slippery before you take a single step. The wetness comes first. The pressure comes second. So pressure melting can't be the answer. Fine. Maybe it's just smooth. Smooth surfaces are slippery. Everyone knows that. Except smooth glass isn't slippery. A polished marble floor isn't slippery when it's dry. Smooth and slippery are not the same thing. And if you look at ice under a microscope, it isn't even that smooth. It's full of tiny ridges and crystal boundaries. Smooth doesn't explain it either. So here you are, a thing you have encountered thousands of times in your life. A thing so ordinary we make jokes about it, build entire sports around it, complain about it every winter. And the real explanation, the actual physics, was so hidden, so genuinely strange, that it took scientists until the 1990s to get close to the truth. And when you hear it, I promise you this, you will never look at a glass of ice the same way again. But before we get to the real answer, we need to do something. You need to feel what's actually happening, because understanding ice starts not in a lab, but in your own hand. The experiment you can do right now. I want you to do something. Right now, if you can, go to your freezer. Take out an ice cube. If you can't do it right now, that's fine. But really picture this as I describe it. Hold the ice cube in your palm. Don't squeeze it. Don't rub it. Just let it sit there, completely still. What do you feel almost immediately? Cold, obviously. But also, wet. Your palm starts feeling damp within seconds. A thin film of water appears right at the contact point between your skin and the ice. Where did that water come from? Your first instinct is probably, my hand is warm. My body heat melted the surface. Reasonable. Makes sense. Except, try the second part. Now take a frozen metal spoon straight from the freezer. Same temperature as the ice. Press it against your palm the same way. The metal feels colder. Much colder, actually. Metal conducts heat away from your skin faster than ice does. But here is the thing that should bother you. The spoon feels drier. Both objects are equally frozen. Both are sitting against your warm skin. But one immediately feels wet and one doesn't. If body heat were the full explanation, the metal spoon, which steals your heat faster, should produce more water, not less. It doesn't. So body heat alone isn't the answer. What about friction? Maybe the sliding itself melts the surface? Walk out onto a frozen lake and stand completely still. No movement. No sliding. You still slip. Stationary ice is slippery. There's no friction happening. Nothing is sliding. Nothing is generating heat. Friction doesn't explain it either. So here's what the experiment is actually showing you. The wetness on your palm, that tiny film of liquid between you and the ice, wasn't created by your warmth. It wasn't created by movement. It was already there, sitting on the surface of the ice before you ever touched it. Think about what that means. A block of ice sitting in a freezer at -15 degrees Celsius. No pressure on it. No friction. No heat source nearby. And its surface is not fully solid. There is always something on the surface of ice that behaves like liquid. Not because it's melting. Not because of anything you're doing to it. But because of something strange happening at the molecular level. something that physics took 150 years and quantum mechanics to explain. But before we get there, let's deal with the explanations you were probably taught in school. Because there's a good chance every answer you've ever heard about ice was wrong, and not wrong in a minor way. Wrong in the way that professional scientists believed them, published them, and defended them for decades. That wet film you felt in your hand? It's the key that unlocks 150 years of scientific debate, because explaining where it comes from turned out to be one of the hardest questions in surface physics. 3 wrong answers. Science believed. Here's something nobody tells you when they explain ice. The explanation you probably learned in school, in a textbook, from a documentary, was almost certainly wrong, not a little wrong. Not wrong in the way that simplified explanations always leave out details. Wrong in the way that professional physicists publish papers defending theories they were sure about, and other professional physicists spent careers proving them incorrect. There are 3 main theories that have each had their moment as the accepted answer. Let's go through all 3. And let's show exactly where each one falls apart. Theory 1, pressure melting, the oldest explanation, and the one most people still believe today, is pressure melting. The idea is elegant. You stand on ice. Your weight puts pressure on the surface. That pressure lowers the melting point of ice just enough to turn a thin layer into liquid. You skate on that liquid. Simple. Lord Kelvin proposed this in 1850. He was one of the greatest physicists of the 19th century. The textbooks ran with it for over 100 years. The numbers don't work. Here's the problem. To lower the melting point of ice by just 1 degree Celsius using pressure alone, you need to apply roughly 130 atmospheres of force. That's the equivalent of 130 times the weight of the entire atmosphere pressing down on a single point. A figure skater, even a heavy one, generates maybe 2 or 3 atmospheres of pressure on the blade. That's enough to lower the melting point by about 0.02 degrees, 2/100ths of a degree. On a day when the ice is -10, that does nothing. The ice stays frozen. And here's the detail that finishes it off completely. Ice is slippery even when you're standing still. No movement, no pressure concentrated on a blade, no skating. You step onto a frozen puddle in flat boots and your feet go out from under you. Pressure melting cannot explain that. Theory 1 is dead. Frictional heating friction. Heat pressure doesn't melt the surface, maybe friction does. When you slide across ice, your skate blade rubs against the surface. Friction generates heat. That heat melts a thin layer. You skate on the meltwater. Clean and logical. This theory replaced pressure melting as the consensus explanation through most of the 20th century. It felt more physically satisfying. Motion creates heat. Heat melts ice, of course. But what happens before you start moving? Go back to the frozen lake. You walk to the edge. You step onto the surface carefully, both feet planted, completely still. You haven't moved an inch. You still feel it. That immediate, unsettling lack of grip. The surface is slippery before a single millimeter of sliding has occurred. Frictional heating requires friction. Friction requires motion. There is no motion. Theory 2 is also dead. Theory 3. Vapor layer. The third theory is more obscure, but it had serious scientific support for a time. The idea? Ice sublimates, meaning it transitions directly from solid to vapor without going through liquid. A thin layer of water vapor forms between the ice and whatever is pressing against it. You effectively skate on a cushion of gas. It sounds strange, but sublimation is real. It happens. Ice in your freezer slowly shrinks over months even without melting, but the timing is completely wrong. Sublimation is a slow process. The vapor layer it produces is far too thin and forms far too slowly to account for the immediate slipperiness you feel the instant your foot touches ice. And at very low temperatures, -40, -50 degrees, sublimation slows to almost nothing. But ice at those temperatures is still slippery. Theory 3. Dead. So here you are. 3 theories. All of them proposed by serious scientists. All of them taught as fact at some point. All of them wrong. And if you're feeling a little unsettled right now, good. That unsettled feeling is what real scientific thinking feels like. It means you're paying attention. So what is actually happening? The answer involves something that exists on the surface of ice all the time in your freezer right now. At -15 degrees, that is not fully solid, has never been fully solid, and cannot be fully solid. and physics only discovered it in the last 30 years. That wet film you felt in your hand? It's the key that unlocks 150 years of scientific debate, because explaining where it comes from turned out to be one of the hardest questions in surface physics. The worldview bomb: ice is never fully solid. So 3 theories, all wrong. All believed by serious people for serious amounts of time, which means the real answer had to be something else entirely. Something that wasn't about what you do to ice. Something about what ice already is. And here is where it gets genuinely strange. Ice is never fully solid. Not at -10. Not at -20. Not at -40. The surface of every piece of ice, the top layer, just a few molecules thick, exists in a permanent state that is neither fully solid nor fully liquid. Scientists call it a quasi-liquid layer, or a pre-melting layer. It was theorized as far back as the 1850s by Michael Faraday, but nobody could prove it or explain it properly. It took until the 1990s, when physicists finally had tools sensitive enough to look at individual molecular layers, to confirm it was real. And when they measured it, what they found was this. How thin is this layer? The quasi-liquid layer on the surface of ice is approximately 1 nanometer thick. Do you know how thin 1 nanometer is? A single human hair is about 80,000 nanometers wide. That means this liquid-like layer, the thing responsible for every skating rink, every winter road, every childhood fall in a frozen puddle, is 80,000 times thinner than a human hair. It is almost incomprehensibly small. And it is entirely responsible for one of the most recognizable sensations in human experience. That is not a small thing hidden in a large system. That is a molecular whisper controlling something we experience every winter. Why does this layer exist at all? Now here's the part that requires a small thought experiment. Stay with me. Picture an ice crystal. Inside the crystal, every water molecule is locked in place. It has neighbors above, below, left, right, front, back. Those neighbors hold it in a rigid lattice. That is what makes ice solid. Now picture a molecule sitting right on the surface, at the very top layer. It has neighbors below it. It has neighbors to the sides. But above it, nothing. Empty space. What happens to a molecule that is missing half its neighbors? It cannot lock into the lattice as tightly. The bonds that would normally pin it firmly in place are only pulling from one direction. The molecule has more freedom to move, more thermal vibration, more looseness. It is not liquid. But it is not behaving like the solid molecules below it either. It exists in a strange in-between state, ordered enough to still be part of the ice structure, but disordered enough to flow and lubricate like a liquid. This is the quasi-liquid layer, not melted, not frozen, something in between that has no perfect name. Why quantum mechanics had to get involved here is the part that took the longest to understand. Classical physics, the physics of objects you can see and touch, predicted that this surface layer should disappear at low enough temperatures. Cool the ice down far enough, and eventually the thermal energy drops so low that even surface molecules lock into place. But that is not what happens. Experiments showed the quasi-liquid layer persisting even at -40 degrees Celsius. Even at temperatures where everything should be frozen solid. Why doesn't it freeze completely? Because at the scale of individual molecules, quantum mechanics takes over from classical physics. Quantum mechanics introduces something called zero-point energy. Even at absolute zero, the coldest temperature theoretically possible, particles are never truly still. They always have some residual vibration baked into the fabric of reality itself. At the surface of ice, where molecules already have reduced bonding holding them down, that zero-point vibration is enough to keep a thin layer permanently mobile, permanently liquid-like, permanently slippery. You are not slipping on ice because of pressure, not because of friction, not because of vapor. You are slipping because quantum mechanics will not allow the surface of ice to be fully solid. What this means for the ice in your glass, go back to your kitchen. Take that ice cube out of the freezer again. The temperature inside your freezer is probably -18 degrees Celsius, well below freezing, solidly frozen by any everyday measure. And right now, on the surface of that ice cube, there is a layer 1 nanometer thick that is not behaving like a solid. It was there before you opened the freezer. It was there last night. It will be there every moment the ice exists. Not because anything is wrong with your freezer, not because the ice is starting to melt, because that is what ice is. Ice has never been fully solid. We just didn't have the tools to see it until 30 years ago. And here is the thought that should sit with you as we move into the final part of this. This quasi-liquid layer, this permanent molecular border between solid and liquid, shaped human history. It built sports, defined battles, enabled trade routes, cost lives on winter roads. Entire civilizations were built around managing something that physicists could not explain until 30 years ago, and that exists in a layer thinner than a single virus. And the fact that we figured it out at all, that humans looked at a frozen puddle and refused to stop asking why until quantum mechanics gave us the answer, that is the part of the story nobody talks about. What ice teaches us about knowing things. Ice changed everything. We just forgot. Before we had refrigeration, ice was one of the most valuable commodities on Earth. In the 1800s, the ice trade was a global industry. Workers cut blocks from frozen New England lakes in winter and shipped them to cities across America, to India, to South America, to the Caribbean. Ice houses kept it insulated for months. Ships carried it across oceans. Armies have won and lost battles because of ice. Supply lines froze. Soldiers lost their footing. Napoleonic campaigns failed partly because of what ice and frozen ground did to movement and logistics. Speed skating, ice hockey, figure skating, the bobsled, entire sports that millions of people watch and love exist because of a 1 nanometer layer of quasi-liquid that physics couldn't explain until 30 years ago. Ice didn't just affect history. Ice was history. For centuries, the most familiar things are the least understood. Here's the thing that I want you to sit with. Of all the phenomena in physics that were mysterious and unsolved, ice was not supposed to be one of them. Gravity, dark matter, quantum entanglement, those we expect to be puzzling. Those are obviously hard. They involve the edges of what we can observe and measure. But ice? Ice is in your freezer. It is in your drink. It falls from the sky. Children play with it. We have been surrounded by it for the entire history of our species. And we couldn't explain why it was slippery until the 1990s? Yes, because familiarity is not the same as understanding. Because the fact that something is ordinary does not mean it is simple. Because the most common things in your daily life can hide physics so strange that it requires quantum mechanics to explain. The universe does not become less mysterious just because you've seen something 1,000 times. Remember that ice cube? Remember that ice cube you held at the start? You pressed it into your palm. You felt it go wet immediately. You asked where that water came from. Now you know. It wasn't your body heat. It wasn't melting. It wasn't anything you did. That wet film was already there. A permanent quasi-liquid layer, 1 nanometer thick, held in place by zero-point quantum vibration. By the fact that at the surface of ice, the laws of classical physics hand over to quantum mechanics, and quantum mechanics refuses to let things be fully still. You weren't touching ice in the way you thought you were. You were touching a quantum boundary, with your bare hand. In your kitchen, humans figured this out. That matters. 200 years ago, people slipped on ice and had no idea why. 150 years ago, Lord Kelvin took a guess. He was wrong, but he was asking the right question. Decades of physicists argued, measured, proposed, and failed. Not because they were bad scientists, but because the answer required tools and theories that didn't exist yet. And then, in the 1990s, we built those tools. We looked at the surface of ice at the molecular level. We found the quasi-liquid layer. We traced it back through quantum mechanics and surface physics, and finally, after 150 years, we understood. Not because someone was especially brilliant. Because people kept asking why. Because scientists refused to accept it's just slippery as an answer. Because the question was treated as worth pursuing even when it seemed trivially obvious. That is what science actually looks like. Not eureka moments, not genius. Persistence. Curiosity. The refusal to stop at the comfortable answer. That is one of the greatest things about being human. We look at a frozen puddle and we can't leave it alone. So next time you slip on ice, or catch yourself just in time, heart pounding, arms out, don't be embarrassed. You just made direct physical contact with a quantum mechanical phenomenon that stumped physicists for a century and a half. A layer 1e25's, the width of human hair, reached up from the surface of frozen water and reminded you that reality is always stranger than it looks. That's what ice really is. not frozen water. A quantum boundary. And it's been hiding in plain sight your entire life.